This is noise due to the random motion of, we usually think about it as electrons within the instrumentation, right? Within those circuits, we think about electricity as electrons flowing through a current, right? But those electrons are not like water in a water hose, right? They just don't go one direction. They have some random motion associated with them. And so they don't always travel the direction of the current. There's a small, little, maybe it's 1,000 steps forward and 1 step back, right? They flow pretty well, but there's this just tiny bit of noise due to the random motion of those electrons. And of course, how's this going to change with temperature?
We're going to have more thermal noise as temperature increases because the kinetic energy increases.
Yeah, more kinetic energy, more random motion. And so this increases with temperature. That's why we call it thermal noise. Right? The equation for thermal noise, so the RMS voltage for thermal noise, RMS, do you know what that means? Root mean square. You talked about it in probably PChem with speeds. We talk about it in Gen Chem with speeds, but I know that was a long time ago. It's the square root of the average of the square of whatever we're talking about, right? And so it's just a way of taking, it's a little bit different from a straight average. It's just a little bit different way of thinking about it. So this RMS, this root mean square voltage for thermal noise is given as the square root of 4 times Boltzmann's constant, K sub B, times the temperature, times R, that's our gas constant R, right? And then delta F. This delta F we talked about a little bit on Monday, right? This is our bandwidth. Right? So what range of frequencies are we actually measuring? What range of frequencies get through? We'll talk a little bit more about that in just a minute when we talk about rise times of response rates. Okay. If we want to measure more of a particular spectrum, right, we're going to increase that bandwidth. And so the more of a spectrum we want, like say we want the whole UV vis spectrum, that's going to be 1,000 nanometers max, something like that. If you want a really wide bandwidth like that, then you're going to have increased thermal noise. So it doesn't depend on the frequency of the measurement. It depends on the frequency of what's being measured, right? So we want to reduce our thermal noise as low as possible. We're going to reduce our bandwidth, reduce our temperature. Okay. Shot noise, moving to the second one. Shot noise comes from the quantized nature of electrons and photons. Right. We call this shot noise because if we think about an electron hitting a detector or a photon hitting a detector, we can think about those as sort of individual shots, right? If we have something, again, I use UV vis because hopefully you're relatively familiar with it, but if we have a pretty dilute compound where our absorbance is low, there's a whole lot of photons that make it through that sample, make it through the instrument, hitting the detector at the same time, right? If I have 1 trillion photons hitting the detector, if there's 1 or 2 more or less every second, doesn't really matter. There's 1 or 2 million more or less every second. Doesn't really matter if I have 1 trillion photons going. But if I have a particularly concentrated solution and very little light is getting through to the detector, and say there's only 1,000 photons hitting the detector, if I'm missing 1 or 2 photons or even 10 photons, you're talking about 1% difference. And so the shot noise comes from the fact that it's not a continuous, the flow of photons and the flow of electrons is not a continuous thing. They are these individual particles, and there will be some fluctuation in how many of them get through the instrument and to the detector. Again, hopefully it's not a big fluctuation, but this is going to be more important when we have low signal. Important. Noise is never important. More noticeable. Because we think about shot noise as being these electrons hitting a detector or electrons flowing through a detector, instead of voltage, it's given in current. And so the equation for the RMS current for shot noise is given as square root of 2 times I times E, little e, that's the charge of an electron, again, times that bandwidth. Okay. And so this here, this I is our DC current. Okay. And so again, if we want to reduce shot noise, we want to have a lower bandwidth, right? And we want to increase our current, right? Shot noise is one of those things that is noticeable. It's always noticeable. It is a larger fraction of the signal when we have a small amount of signal, but it does increase, as you can see, with the square root of the overall signal. Right? That DC current is almost always related somehow to our analytical signal. And so it does increase with the square of the square root of that current. And so it doesn't increase as quickly as our analytical signal does, but does increase with analytical signal. But it's more noticeable when we have a small amount of signal. This flicker noise, 1/f noise, is something that, as smart as we are, we still don't have a very good explanation for. This flicker noise, it really is just 1/f noise. Right? This is noise due to the frequency of the measurement. Right? I'm going to go on to the next slide because that has a little chart on it. Right, this 1/f noise, what you can see is that we don't know exactly what it is. This diagram is from our textbook, and what they're trying to show you is this plot here is the curve of 1/f. And these shaded regions both correspond to about 1 hertz, right? Because our x-axis here is logarithmic, right? From 0.01 to 1, that's about 1 hertz, right? This little window here is probably a lot more than 1 hertz, if I had to really be guessing, because we're going from 100 to 10,000. And so if I really had to guess, that's probably like 50 hertz, but I don't know. They probably just didn't want to put a line in the textbook. Right? But if we think about the amount of noise due to this 1/f component, it's just the area under the curve for that bandwidth. And so we have a huge amount of noise at low frequencies and a D90 amount of noise at higher frequencies for the same bandwidth. Right? And so, of course, in order to reduce this 1/f noise, we want to use higher frequencies. To avoid that. That one's pretty straightforward. Again, because we don't understand it exactly, we don't have a great equation for it. 1/f, right? There you go. The last source of noise that we'll talk about, the last source of noise that we'll talk about is this environmental noise. Again, this isn't something that we have an equation for because we can sort of pinpoint its origin, right? Some of the main ones that we're interested in usually are these in here, right? For the US, our alternating current coming out of the wall when you plug something in, it's 120 volts at 60 hertz. And so that 60 hertz frequency, if you're trying to measure something there, you're going to get a whole heck of a lot of noise, just because that's where our line voltage is. You see here that they also has the harmonics of that. So 120 hertz, 180 hertz, 240 hertz. These are AC frequencies in other parts of the world, but also if we're trying to measure something at 60 hertz, at 120 hertz, but 60 hertz is our line voltage, then we're going to get some interference there as well. Some of these we might not think about a whole lot. You know, this one in particular, if you're taking a relatively long experiment, right? Say you're averaging an NMR over a couple of hours. If students are walking past the NMR and causing vibrations every 50 minutes, you're going to have some noise that's on a very long time scale that that can affect your measurements. Out here at the higher frequencies, right, AM radio, TV, we, when I was in college, I did an RU in New Orleans, and we were looking at some radio frequency stuff with magnetized nanodots. It was a very physicsy RU, but we had to be careful about which frequencies we used because we didn't want to pick up the actual radio station. And so it may seem that we have some only very narrow regions where we can actually take data, but it turns out that for most of what we're talking about, our frequencies are way out here, right? If we're talking about UV-Vis, again, for example, we're talking about 10 to the 14 hertz, not 44, 10 to the 14 hertz. Something like that for UV-Vis. And so the spectrum out there is a much quieter for environmental noise. Okay. So how does this affect what we do? How does this affect taking a measurement? Well, really what we care about is that signal to noise ratio. And we talked a little bit at the beginning in chapter 1 about how a signal to noise ratio of 3 is our limit of detection. Right. Who remembers what limit of quantitation was?
Is that for like the analytical chemist?
That's right.
10.
That's right. Yeah, and so we need a signal to noise of 3 in order to say, yes, that is a signal, and a signal to noise of 10 to go, I can tell you how much signal that is, right? That's essentially what these two mean. Often when we look at a particular instrument signal like we see here, we use a bit of a shortcut, assuming, the shortcut assumes that the noise is distributed in a Gaussian fashion, right? That it corresponds to a normal curve. And with that being said, the total range of noise corresponds to about 6 standard deviations. Right? Right? Because if we think about a bell curve, a Gaussian curve, plus or minus 1 standard deviation is 68%, plus or minus 3 standard deviations is 99.7%. And so that 6 standard deviations gives us most of the noise, and that's the assumption we use most often. So when we think about signal to noise ratio, we're talking about the average signal divided by the standard deviation of the noise. And so, I don't know, somebody estimate what that standard deviation might be for this example. Julie?
You saying asking for the average signal?
The standard deviation for this noise, If that is 6 standard deviations, what's the average what's the standard deviation for the noise there?
Would it be 25?
I'm okay with 25. Yeah, right. So he said 6 standard deviations was 150. And so 1 standard deviation must be 25, right? And then our signal is up here at, say, 350, right? And so for this particular one, we have a signal to noise is 350 divided by 25. That should be 14. And so this signal is enough out of the noise that not only can we say, yes, it exists, it is signal, not noise, but we can actually start quantifying it, right? Because it's above that signal to noise ratio of 10.
Why did you use 350?
So, because the signal, well, instead of what? You were going to say something.
Like, do you not have to find an average of what, or do you use the P?
So the average signal that we're interested in, and so what we're saying is that this is all noise, right? All this is noise, and that this is our signal.
Okay.
And so the average signal height is 350 here. And the rest of this is noise.
Dr. Davis, if we get a graph like this, however big the signal is, then it's always going to be 6 standard deviations and then divided by 6. And then that way we get what our standard deviation of noise is.
Yeah, you can always use this, this kind of shortcut to figure out what the standard deviation of the noise is. The textbook calls it, in one of the problems, I think it calls it the 99.7% criterion or something, which seems real fancy for what we're talking about, but it's a good assumption to use almost always.
If we have like multiple analytes, how, like we would have 2 separate signal to noise rate, right? If we had 2,
Absolutely.
we'd have 2 different, and we'd have to make sure we know like which peaks of signal correspond to which analyte.
That's right.
And average those separately.
Right.
Okay.
Yep. Yeah. And so in this one, it's easier to see because we're looking at sort of a single peak. Sometimes our signal is, a wave. And so we look at what the average is for the peaks of those waves, right? Rather than this single peak here. And so that's really where the average signal comes from. Okay. All right. So how can we make it better, right? How can we say I want to start using this signal to noise. This is garbage. The controls on my little pin display switched, and I haven't switched them back. This particular signal is really lousy, right up here in this inset. And so our textbook tells us this is 1 scan. But it's good enough that we see there's something there, right? And we want to see what it is. But in order to really tell what it is, we're going to have to improve our signal to noise ratio. It turns out that the improved signal to noise ratio, so S over N within additional averages, is equal to the square root of N times our original signal to noise ratio, S over N naught. And so N equals the number of additional measurements. Okay. This method is called ensemble averaging. Because instead of averaging over just a particular peak, we're averaging the whole spectrum that we get, right? And so we're averaging all of these data points together. Again, if we think about our noise being following that Gaussian distribution, being random, then sometimes at a given frequency, that noise will be positive and large. Sometimes it'll be negative and large. Sometimes it'll be positive and small. Sometimes it'll be negative and small. And so the more times we take a measurement, if we average those together, the more likely it is that that noise will start to go to 0, right, as we average it. And so, again, this is in the inset here is 1 scan. This is 50 scans. Okay. And so we spent a little extra time getting a few more measurements, but it has paid off in dividends in terms of signal to noise. Who wants to, let's estimate this signal to noise here. From there to there, that's about, what, 6-ish, maybe a little more. But let's say that our standard deviation is 1, right? And our signal is up here at, I would say, 9, right? And so here we have a signal noise ratio of 9 to 1. Which, you know, doesn't sound too terrible. We know that it's there. It's a little small for us to quantify right now, right? But by doing this 50 scans, additional scans, so let's see, we want to figure out what our new signal to noise is. So we're adding 49 scans, right? So that's the square root of 49 times 9, right? We said our initial signal to noise is 9. And so our new signal to noise with our 49 additional scans is just 7 times 9. So we have 63 is our signal to noise. And we could probably figure that out by looking, right? If we said that this is maybe 2/3 total. So then 2/3 divided by 6 is 1/6. Two-thirds is 4/6 divided by 6. It's a tiny fraction. It's a tiny fraction. And then our signal actually looks a bit lower, but that's because our noise is up here, right? And so our average is somewhere around 8 now, but we have 8 divided by something small. Let's say it's 1/8. And that gives us 64. That's pretty close, right? Okay. So ensemble averaging is by far the most common way of improving signal to noise ratio. When you take an NMR and you say that's not good, let's take 72 more scans, right? All you're doing is averaging those 72 scans with whatever you took the first time. Section 4 in our text does go into some a little bit more modern methods of using computation to sort of pick out a peak and average just around that peak, and talks about boxcar averaging and Savitsi-Gallais smoothing, and these are all techniques that we can use to try to get rid of some noise. But we're not going to go into those because I like to focus on the actual instrumentation rather than the computational part of things. If you like that sort of coding stuff, by all means, read section 4. But I like the nuts and bolts stuff rather than the computational stuff. All right. The last thing to talk about then is this sampling rate and talking about the Nyquist frequency. So when we look at sampling, let's say we have this particular signal here. This signal's at 4 hertz. I'm sorry if that's small. This image is from our text. It's kind of a bulky image. I didn't want to make it too big on the screen and have some of it get cut off. So the signal's at 4 hertz. What the Nyquist frequency, what Nyquist told us is that we must sample twice as fast as the highest frequency in the signal. Right? And so if we have a whole range of frequencies, we need to sample twice as fast as whatever the highest frequency is for that particular signal. If we look here, 4 hertz, this first scan is at 200 hertz, right? And so for every wave, how many data points do we have? 200 divided by 4.
50.
50.
50. Excellent. And so each wavelength has 50 data points. It's so easy to see what frequency that should be, right? But that's 25 times what the Nyquist frequency should be, right? Nyquist frequency should be 8 hertz, right? And so ostensibly, we should be able to see something that looks like our curve if we only sample at 8 hertz, right? So this is just 8 hertz. Again, remember, Nyquist requires twice as fast as the frequency, so we only need 2 data points for every wavelength, and that's what we have here. Now, this one is nice that you can see that it measured exactly at the peak and at the trough, right? But that isn't necessarily where it has to line up. It's just easiest to visualize it. And so when we try to connect those dots, we get back our 4 hertz curve. Are there other curves that could fit this? Yes, but they're going to be multiples of 4 hertz. And so they're going to be much higher frequencies. The Nyquist frequency tells us that it needs to be twice as fast as the fastest frequency. So it won't be any higher than 4 hertz. And so when we go to sort of trace these dots and figure out what the frequency is, the assumption is always that it's going to be a lower frequency curve than what is written rather than a higher frequency curve. Is that making sense? For example, let me just, it's going to be real bad, I'm sorry, but it's going to hopefully show this. So if this is an 8 hertz curve, I could fit a 16 hertz frequency to it, right? by only matching up every other peak and trough, right? But that's not how Nyquist works, right? The sampling is faster than your actual signal, so I'm not going to fit it with something that's faster than the sampling rate, right? And so this is a no-go. Don't do that. Okay. In the next example here, they sample below the Nyquist frequency. So again, the Nyquist frequency is 8 hertz for this particular curve. Here they sample at 5 hertz. Right? And you can see that, well, if I try to fit that to a curve, it's not going to be the curve that I started with. It's going to be this curve because it's got to be lower in frequency than the sampling rate. And so it turns out this is a 1 second on our x-axis. It turns out this is 1 hertz that it came up with. Right? Again, it's going to be a multiple of 4. So we have 1 times 4, 2 times 4. So we want to always be sure that we are sampling at the Nyquist frequency or faster, right, for these to make sure that we don't miss anything. If we miss something like this, right, that's called aliasing. And so aliasing is, our textbook calls them ghost frequencies. And these ghost frequencies that are due to poor sampling rates. One of the biggest issues with aliasing that may be more common outside of science is in music. If we look at an actual audio signal, that black curve would be the actual sound wave, right? And so that would be something that you might get with a vinyl record, right? Vinyl is very good at reproducing those sound waves exactly. And then when you move to CD, you can see that you lose a lot of that definition. You lose a lot of that accuracy in that tonal quality. And so you see we never get to this point up here because our CD only averages across a certain amount of the curve. We never get to this point down here. The light blue line, I don't know if you can tell that, is DVD. It has a smaller, we call them bins, that it averages across, right? And so you get better reproduction with a DVD bin than you do with a CD bin. This is all about analog to digital converting. Right. Again, that gets a little bit into the electronic side of things, but it's a good example of aliasing where if you don't sample fast enough, you're going to end up with frequencies that are missed, right? So this is a 10 kilohertz signal. You can imagine if we had a 20 kilohertz signal, the bin size for CD or DVD doesn't change, right? And so it's going to be missing more of those highs and lows because it is, it's going to be averaging across more of a wavelength. All right. I feel in my heart that I have missed something. Oh, yes. About bandwidth. I need to add a slide. Can I add a slide? Nope. Let me add a slide real quick so I can talk about sampling. All right, so I told you I'd talk a little bit about bandwidth. Here we go. The rise time, we can think about this also as the response time. Right. This isn't for, again, UV-Vis is the one that you were maybe most familiar with. For UV-Vis, this is not a big deal, right? You put your sample in and you wait for it to stabilize, and it's okay if you have to wait 3 or 4 or 5 seconds, right? How quickly that instrument responds is not of real importance. For something where we're maybe measuring kinetics, though, we want to know if that signal goes down quickly because we want to know what that kinetics measurement is. And so we want an instrument that can respond fast enough to actually get that change in concentration due to the kinetics of the experiment. And so we want to sort of have the best response time as possible for certain instrumentation. And that response time, T sub R, is equal to this 0.35. Again, our text goes into this derivation if you really want to see where it comes from, but I trust mathematicians, divided by that bandwidth, delta F. And so if we are interested in a larger, wider bandwidth, I remember a wider bandwidth means we're measuring more frequencies at once. That's an important part of this. If we change frequencies and take another measurement, the bandwidth doesn't increase. It's measuring all these frequencies at once. Means, so if we have a wider bandwidth, what happens to our rise time?
Decreases.
Yeah. Right. When we talk about a rise time, let's draw a little diagram here. This is time, and here we have our voltage. If I have a good rise time, then that increase is going to happen pretty quickly. Right? This is a short T sub R. If I have a longer rise time, it might look like this. And I have a longer T sub R because what we're measuring, the definition our textbook uses is from 10% of the voltage to 90% of the voltage, right? This time is the time we're measuring. And this first one, it's almost instantaneous, right? It's a millisecond, maybe, right? But for this second one, from 10% of the voltage to 90% of the voltage, we're talking about a pretty significant rise time, right? So if this is maybe 1 millisecond, I would say this is maybe 20 milliseconds. Right? And so you won't get data as quickly if your instrument can't respond fast enough. And so thinking about this rise time in terms of bandwidth and then relating it to thermal noise and shot noise, which we saw also included bandwidth parameters in it. So we can sort of relate an increase in rise time, an increase in response time to changes in thermal and shot. I've added 4 homework problems from chapter 5 to our Moodle page. This is the end of material for exam 1. That's Tuesday. Right. Monday, we are going to jump into chapter 6, which talks about spectroscopy, moving into UV Vis. Tuesday, we have our exam. And then just so we're all on the same page, well, I will likely try to switch to video lectures as the due date approaches so that I can have those made ahead of time and just sort of send them out to you. Right? All right. Let me know if you want to meet for office hours, anything like that. And I hope you have a joyous weekend.
Bye. Thank you.
Bye.
Ta-ta.
Yeah.
Davis,
Labs due at 5.
Oh my gosh,
Guys?
I have to start that.
Can I
Okay.
ask you some questions about the lab?
Please do.
All right. Sorry, I was just like sending a bunch of emails. I don't know. It's just been kind of a stressful week.
No, it's really okay.
But
I'm sorry to add to your stress.
no, it's okay.